Okay, so we'll start today with a reminder of our internship opportunities at Argonne. I think Kyle showed you these slides in December. Argonne is planning on having in-person interns this summer, although there's also the option to be virtual depending on the project. And this is all pending how the pandemic goes. But so there's lots of opportunities to have events with other interns. And we have a variety of different programs. So this is just recapping these categories that Kyle showed you earlier. And I wanted to remind you that these deadlines are coming up. Generally, we have like a hard deadline of March 1st. And some of these rows are too late for this year. You could have them in mind for next year, but this last one, undergrad seasonal intern, you could still apply for. And then I talked to my teammates at ALCF, the supercomputer division at Argonne, to see what kind of intern projects they have this summer. So disclaimer, we're waiting to get these approved in a few days. So I say they're potential projects. And you've met most of us through this training. Hui Ho, who presented about distributed training recently, he will hopefully be supervising an intern about data management and IO benchmarks on our AI testbeds. So these are like novel AI hardware that's specially designed for deep learning. Corey, who presented to you about autoencoders and GANs, he is hoping to hire an intern about continuous integration and performance benchmarking. Dennis Boyda is looking at scaling transformers and convolutional neural networks with the different frameworks for data parallel deep learning. So there's Horovod, PyTorch DDP, and DeepSpeed. And this would be on Polaris, which is our new supercomputer, the number 12 supercomputer in the world. We should be available to interns this summer. And I'm hoping to hire an intern to add some features to DeepHyper, which Prasanna will be showing you today. And then next week, we'll highlight some other opportunities for internships from other teams. And I just want to remind you the deadline is March 1st. I put our emails in case you want to ask more about these projects, but you do have to apply on the Argonne website. So that's all I have for intern slides. So now I want to introduce Prasanna. Prasanna Balaprakash is a computer scientist at the Math and Computer Science Division here at Argonne, and he's also has a joint appointment with us at the Leadership Computing Facility. And he's been working on AI, machine learning, optimization, and high performance computing for a huge variety of application areas. And a big part of his research is related to this hyperparameter search and neural architecture search through DeepHyper, which he will be teaching you about today. And take it away, Prasanna. Thank you.
Right. Thanks, Bethany. Do you hear me okay?
Yes, it's great. Thank you.
Okay, great. So the slides are fine, right?
Yes, they look great.
Okay, excellent. Yeah, good afternoon, everyone. My name is Prasanna Balaprakash. As Bethany introduced, I'm a computer scientist at Argonne. And today we will be covering hyperparameter search. In particular, a special focus will be on the software that we are developing here at Argonne for hyperparameter search and the neural architecture search, which is sort of another version of hyperparameter search. We'll see how much we can cover with hyperparameter search in terms of the notebook, and if we manage to finish a little early, then we can also go into the neural architecture search tutorial. So the way that I'm planning to cover this material is first I'm going to give a high-level overview of hyperparameter search and DeepHyper. What are the components of DeepHyper and how this hyperparameter search tasks can be done with DeepHyper. Okay. Please feel free to stop me, interrupt me if you have questions. I would really like this to be interactive, and unfortunately we are in Zoom, but if you can raise hands or post questions in the chat, Bethany or someone will be able to interrupt me and ask those questions. So please feel free to do that. Okay. Okay, so you have seen several lectures on deep learning, right? So different types of neural networks, because each of these we need different types of neural networks because the scientific applications and the type of data sets are diverse, and we often need to identify and come up with the right type of architectures. Okay, so what is the major issue? The major issue is, deep learning or deep neural network, is sort of complex to design, right? So if you already have an architecture which is designed by someone, fine, we can take it and apply it. But in many scientific applications, that's not the case. One needs to sort of, do this from scratch. And to give you an example, right? If you ask like why convolution neural network looks like that, right? So why the filter size is like that, why the convolution size is like that, you will not often find the right answer, because often these are sort of result of various manual trial and error process, coming up with the right values for convolutions and right values for pooling and so on and so forth, and even take the learning rate, batch size, etc., etc. So the number of degrees of freedom in designing neural networks are many, right? So that's a challenge. Even if you take the simple graph neural network that is shown on the left side, it's a message passing neural network followed by the dense layers, and then you can just add skip connection wherever you want. Even for this simple neural network, you can end up with a million possible designs, more than a million possible designs, right? So that is like, okay, so you have a lot of building blocks, right? So what the building blocks are. You have to put the layers together and you have to connect those layers. But the number of possible designs that you can think of is sort of it's exponential with respect to the number of design variables that you deal with. So that is the challenge, and often what people do, experts do, is try to put them together and then try to do this in a manual way, trial and error, ad hoc, based on the previous experience, or look at the paper, how people already did this, and they just basically copy paste those tasks, those architectures, and go about it, right? So that's the sort of common practice, and it works well if it is a well-known task, like, okay, you want to do image recognition, fine, people have spent several years on that, and good values for that, so you can do that. But if you're dealing with a new set of tasks, or completely a new type of data or modality, then you often have to design these networks manually, and it takes time. So to illustrate this fact, you can also go and play with this TensorFlow Playground. The link is shown here, HTTPS Playground. You don't have to do that now, but this is a fun way to sort of go and change the architectures, the neural network architectures, and change the hyperparameters like learning rate, activation. So you can just change this and see for this particular data set how your loss changes, your training loss and testing loss. So hope you can see my okay, not this. Okay, anyway, so you can see the how the training loss and testing loss sort of progresses, right? So this is for a simple neural network with four with four hidden layers, and you can sort of configure the number of neurons per layer and change the learning rate and other hyperparameters. And what you can do is, on the same network, you just go and change only one. You add one more neuron. Now you see like all four neurons in each of the hidden layer, and you can go and see how the training loss and testing loss changes. It's drastic, right? For the simple data set, for the simple neural network, just by adding one neuron, you basically change the loss landscape to a large extent, and your training loss and the testing loss are totally different, right? So it's 0.3, right? So test loss is 0.3 here, and here you see test loss is 0.06. Just by adding one neuron, you reduce the loss by an order of magnitude, right? So that's, so that's the sort of importance of finding the right parameters for a given neural network that you are trying to design. So at a high level, the degrees of freedom can be sort of, classified into two groups. So one is algorithm hyperparameters, where you say, okay, the optimizers, right? Often you use one optimizer over the other, and there are some sort of rules of thumb which optimizer to use. But often, don't trust those, right? So always you play with different types of optimizers and see which one is best. So if you're thinking about algorithmic hyperparameters, you have different type of optimizers such as stochastic gradient descent, RMS prop, Adam. Learning rate, again, it can go anywhere from 10 to the power minus 5 to 0.1, and often this is depending on the type of loss surface that you are dealing with. Batch size, mini batch size, learning rate scheduler, adaptive batch size. So these are all, let's say, the neural network is fixed, right? And the way that you optimize the weights in the neural network changes based on this algorithm hyperparameters. Okay. And you also have the second group, which is architecture variables, right? So it's basically changing the architecture itself, right? You can have a five-layer network, a 10-layer network, or within each layer you can use, if you're talking about LSTMs or dealing with time series, you can use different types of LSTMs. Sorry, this is automatically changing. Sorry. And so on and so forth. So then the type of the layer, fully connected, convolution, recursive, or whatsoever, type of activation function, dropout, and more importantly, skip connections, right? So you can, if you have, in one of the tutorials this was covered, right? So the ResNet type architecture where you connect different layers, right? And why skip connections are important? Because skip connections make the loss function pretty smooth, right? So you might have rugged loss function, and as soon as you add skip connections, your loss function become really smooth, and your optimizer can really, optimize well on those type of surfaces. So that's why skip connections are really, really important in modern neural networks. Okay, so there are two different types of, there are two classes of parameters that you can change to design the network. Going next. So mathematically, this can be formulated, the whole problem of finding the right parameters for the given neural network can be then, can be cast into this bi-level optimization problem. The low-level optimization problem is the one that you have seen so far. It's all about, given a network, I want to find the right weights, right? So weights, how to train, and so on and so forth. So that's with the training data. That's a lower level problem. But the hyperparameter search and the architecture search that we are talking about is one level higher than that. So for a given hyperparameter and a given architecture variable and algorithm hyperparameter, you go and solve the lower level problem, right? So it's essentially, so far you are talking about training only once. Now you are talking about training thousands of models because you want to explore thousands of hyperparameter combinations to find the right hyperparameter configuration that gives you the best validation loss, because the upper level problem is always, you deal with the validation data. So you minimize validation loss in the upper level problem, whereas the lower level problem uses the traditional loss on the training data. Okay, so that is a key difference. So far, the focus is on the lower level problem. Now we are going to focus on one level higher, where we will be optimizing the architecture and the algorithmic hyperparameters such that you get good validation loss from that model. Okay, so that's the key difference. Okay, so this is not an easy problem, right? So if you are dealing with just 10 hyperparameters, yes, you can just write a Python script and run 10 models and be done with it, right? So depending on the data size, you can easily do that, right? But even with a handful of hyperparameters, you are talking about exponential number of possible configurations, right? 10 parameters with 10 different values, you are talking about 10 to the power of 10 different 10 to the power of 10 different possible choices, right? So or 10 to the power of 10 algorithmic combinations. So here you cannot enumerate. You cannot enumerate all possible configurations, even with the exascale machine for a reasonably large neural network. You cannot exhaustively go through all possible hyperparameter configurations. So that's why you need a more sort of a smart search that sort of navigate the search space and find right hyperparameters in a reasonable time. Okay. So we have been developing software for that. It's called DeepHyper. You can see the documentation link here, and we will be covering this in the tutorial today. DeepHyper consists of two components. So one is the search component, where we will be talking about different types of algorithms that will be used to search those hyperparameters and neural architecture variables. Okay, so within hyperparameters, to search hyperparameters, we use various types of algorithms. We will be focusing primarily on the Bayesian optimization method, but there are other sort of methods available for use, but those are not as effective as the one that we have on the Bayesian optimization. So some of the existing tools, if you go and look at AutoKeras and other things, they use random search, grid search, and things like that. These are fine if you are dealing with few parameters and few possible values, and sort of tie data set, tie architecture, that's fine. Or if you know already good configurations and you want to get marginal improvement, that's fine. But if you want to deal with really large number of parameters and large number of possible choices, then you have to do something with Bayesian optimization, and more importantly, at scale. The second component is neural architecture search. So this is about searching over architecture space, which is much more difficult than hyperparameter search, because hyperparameter search, you can sort of say, I know all the variables, right? So these are often static and fixed. Whereas the architecture space, it's much more complicated, because you have to search over which type of skip connections I need to put and where to put, and so on and so forth. It becomes really difficult, and many of the existing algorithms are typical out-of-the-box algorithms do not work for that. So we have been developing some sort of customized algorithms for doing neural architecture search. And we also have neural architecture and hyperparameter search joined, in the sense, there is one algorithm that searches for hyperparameters, and also the architecture hyperparameters jointly. And we use various types of algorithms for that. And one thing which we will not cover, but I'm happy to provide references. One thing is you have attended the distributed data parallel training course, right? And often, and you might have found out, like, the key there is to adapt your batch size and learning rate, right? If you adapt your batch size and learning rate, you can reduce your training time significantly. So what we do is we do hyperparameter search to automatically adapt the distributed training parameters, such as batch size and learning rate, while doing architecture and hyperparameter search. So we can essentially reduce the time to train each model within hyperparameter search. Okay, so these are all great, right? But the point is, we have to do this at scale, right? So if you try to do that on a single node, the number of possible architectures that you can explore is rather tiny given the search space. The search space that we are talking about is like billions and billions of configurations, billions and billions of neural architectures. And if each of your training takes 1 hour, you cannot, even explore a tiny fraction of that search space. So that's why we have to scale this. All these algorithms need to scale, in the sense that, these search algorithms basically launch a job with thousands of workers, where each worker evaluates or do model training, and sort of communicate that back to the search, saying that, okay, the search generates different parameter configurations. Each worker takes them and evaluates them and give the result back to the search, and based on that, the search learns how to generate even better configurations. And this is done iteratively and in a much more faster way, so that using a lot of nodes, so that we can get high quality models in a very short period of time. So the hyperparameter search, at least for a reasonable size data, we are talking about like in the 6 hours, we can generate really high quality models completely automatically without a lot of human involvement. And when we are talking about scaling, we also have to talk about workflow systems. So these are all critical because the workflow system sort of hides all the complexities of running multiple trainings simultaneously. And we rely on Balsam, Ray, and subprocesses. And recently we are using MPI, pure MPI to reduce the overhead. So there are different possibilities to use different types of workflows to sort of scale this on different types of machines. And some of our collaborators in the university, they just use this and use Ray, for example, to scale this on their university clusters. So there are multiple choices on that front. So as I said, the Bayesian optimization at a high level, this is about, so that at the center of the search, there exists a Bayesian model. Okay, so the Bayesian model, think of this as a predictive model that tries to learn the relationship between the configurations and their corresponding performance metrics. In this case, it's basically the validation loss. So think of think of a predictive model that sits on top of whatever the evaluations that are happening, right? And tries to learn, okay, given this parameter configuration, what is the validation loss? So this is critical because using that sort of model, so this model sort of evaluates these configurations, learn from it, and then sort of try to generate better configurations instead of exploring the space blindly. I don't want to get into the details of it. This is something that we can go through offline, but the high-level idea is shown here. So it's an iterative process where the learning model generates configurations. Each of the configuration correspond to a model training, and those are evaluated in parallel, and those results are given back to the learning model. From that, it sort of learns and then generates a next set of promising configurations and so on and so forth. Okay. The second component is neural architecture search. This is this is about defining a search space of neural architectures, and the way that we define the search space is using a graph. And you can see, like, okay, so if you look at this figure, this is shown here, like, okay, so the input. So from the data, what is the input and what is the output, and you have to define a search space of search space using a graph, where you say your first node consists of different layers. For example, identity means I just take the input and just pass it through the next layer. And LSTM16 means LSTM layer with 16 units, LSTM layer with 32 units. And you can also put GRU and RNN or whatever. So if you're talking about sequential data, right? So different types of units and different types of layers you can just plug in. Okay, you say that node N1 has different possible choices, and you just say what are those choices. And then often we use a dense layer to take those results and project it to the next layer, and so on and so forth. So the other thing is the skip connection. As I mentioned, the skip connection basically says, okay, if I am here, right, LSTM5, what are the possible skip connections that I can make? So either, because I don't need to worry about the node N3 because it's always connected. The possible choices are I can connect to N1 or I can connect to the input, right? And that's exactly what this search space is saying. So I have a node N4, which says create a skip connection from the input all the way to the LSTM. And you say that this as a possible choice, not as a possible definition, right? So that's the key. You want the search algorithm to go and figure out whether to make the skip connection or not. So think of this as a binary variable 0, 1. If it is set to 0, there is no skip connection. If it is 1, then a skip connection is made. And all of them, we create a possible set of choices, and we let the search algorithm to search over this search space. And in the tutorial, you can see in the second tutorial how to define this graph search space. And essentially, it is about creating each node and creating a skip connection node to say where it can, what are the possible connections, and finally saying, okay, what is my output layer? So we'll go through this, line by line in the Jupyter notebook. This is to say, like, this is coming in the sense how to define a search space that captures set of all possible architectures one need to search through. And once you define that, you see it's like just 10 lines of code. Okay, 10 lines of code in Python. Once you define that search space, you can just go and randomly sample, right? So it's like this GANs where you can generate faces, right? Once you train, if you define the search space with the graph, you can then just go and sample without training. You can go and sample from that space. You can different types of architectures, and these are architectures that were generated from the previous example. And this is one with with the different skip connections. And you can see the wide range of architectures that were automatically built, right? Just randomly sampling here, no optimization, nothing. But I want you to take a note at how sophisticated and how complex the skip connections can get, right? So if you ask a human to figure out, oh, I want to do a skip connection from this node to this node, that's not going to happen, because if you look at the ResNet, the skip connections are pretty irregular because that's what humans can do. But now we have power to sort of search over many different possibilities, and that makes this a lot more powerful than human design neural network, right? Even with the simple search space, you can really create sophisticated neural networks, which need to be trained and searched over. That's a different thing. But the possibility that these type of neural networks can be constructed gives a lot of flexibility. Okay, so the way that we search over this space is shown in this cartoon. So we start with some randomly generated configurations. So something like what randomly generated networks, which are shown here. And then it performs regularized evolution. It's a type of a genetic algorithm. And you take the best from the population, and you take a subsample from the population, and then you select the best, and then you do a simple mutation. Right? Mutation is just changing one possible choice. If there is in a particular node, in a particular network, you have one node that has different possible choices, then let's say the previous example, LSTM32, from LSTM32 to LSTM64, that's one mutation. Or another mutation is deleting a skip connection, right? Or adding a skip connection, and so on and so forth. So you perform a mutation, train it, put them back in the population, right? So, and then you remove the oldest one in the population, and you do this repeatedly. And the nice thing about this is the scale, right? So it's completely asynchronous. It's not a block synchronous, which means that as soon as one network result is available, you can do this operation and then send another architecture for training, and you can do that in a massively parallel way. And this matters because here is some result on how things work. So these are all experiments on different number of nodes. So architecture search on 33 nodes, 64 nodes, 128, 256, and 512. And what you can see is on the x-axis is time, and y-axis is the number of unique architectures with R² value greater than 0.96, which is basically looking how many good architectures you can generate with this. And with large number of nodes, you have a possibility to evaluate, let's say 512 nodes. At any point of time, you have 512 model training happening, right? A population size of 512, one of them finishes, you select the subsample, perform mutation, and immediately fill, right? So which means at any point of time, you have 512 model training that are happening. We are not talking about distributed training, but let's say each node has one model training. And what you see here, the number of unique architectures that are generated by the search, and basically, within 60 minutes. So this is on a recurrent neural architecture search for geophysical emulation. It's a LSTM type architecture search, and we could generate within an hour more than 1,500 architectures, 1,500 unique neural networks with R-squared value greater than 0.96. Think about that as a capability, right? We are not talking about generating one best model, one best high-performing model. We are talking about generating thousands of high-performing models. And this gives you a lot of flexibility when you are when you want to pick the best model, or you can perform ensembling, right? So you can take all the 1,000 models and then do an ensemble prediction and use them for many other things like uncertainty quantification and things like that. So that is the power of automated search and automated neural architecture search with respect to, okay, I have one model that need to be trained. I want to get the best performance compared to what you can potentially do by scaling these algorithms and generate this automatically. And in fact, we compared this with other methods, and especially in particular with respect to random search. If you just, without doing aging evolution or reinforcement learning is another search we used. But essentially, this result is saying, like, you need to be smart about how you search. If you just randomly throw dart and try to evaluate, okay, with 512 nodes, I always randomly sample 512 neural networks and train them blindly, you will not get this sort of performance. So that's why you need sort of much more targeted search, scalable targeted search that can do this job. Okay, so the software can work on single node. If your evaluations are simple for toy data sets, if you want to play with, you can definitely do that on the laptop. But we scale it on university clusters. More importantly, our focus is on scaling the software on ALCF machines. In fact, DeepHyper is available as part of the ALCF software stack, data science software stack. So our users can use this to do hyperparameter search and neural architecture search. So although you can do that on a single node, our focus is primarily on scaling this on supercomputers, on doing this for science data sets and things like that. But of course, you can play with the toy data sets on your laptop. Okay, so so the software is primarily myself and Romain Jallet. We lead the design and development, but it's really a lot of developments from the community, the DeepHyper community. Most of them are here. Without their help, we wouldn't be here. So there are a lot of contributions from a wide range of people, from the application to feedback to new module implementation and documentation and so on and so forth. And I would like to take this opportunity to thank the community here at Argonne and elsewhere. Some more references, and some of the papers are still in review, but they are up in archive. But most of this, we did this on science data sets, cancer data set, weather data set, and so on and so forth. So we are still working on many different aspects of DeepHyper. So please watch out for announcements, including transfer learning and other aspects. But the main branch is stable, and you can already download and play with that. Okay, some funding acknowledgements particularly from DOE, ALCF, and our internal lab funding, LDRD. With that, I'm gonna end this presentation. If you have questions, please ask now, and before we move to the Jupyter Notebook tutorial. Okay. Okay, are there other questions before we move to the tutorial?
I don't see any in Slack or in the chat, so
okay.
Maybe keep going.
Okay, great. So, so the drill, right? So you can go. I assume you are all in the logged in, and you can do a Git pull. So there is a new tutorial folder, 08 Hyperparameter Search. If you didn't see it, please do a Git pull. If you are done with the Git pull, then you can go and ask. So you can type in Jupyter alcf.nl.gov. Okay, I need to share the screen here. Okay. Okay. You are all in? Can we start the server? Please speak up if you have issues. Okay, I'm gonna start the server. Theta GPU node, ALCF AI TP. I'm gonna ask for 1 hour. Then I'm gonna start the request.
Oh, if you want to change the queue.
I didn't see this before, but I just restarted before and it worked. Is that what you see? What do you say?
It looked like you picked the AI hacks.
Oh, okay.
Queue.
So
Yeah, this
let me
queue
log
AI
out.
hacks is
Okay.
not ready right now.
Okay.
The single
GPU.
GPU.
Yeah, sorry. I think I made a mistake there. 60.
That's good.
So question to the participants. How many of you tried to tinker with learning rate, batch size when you did the previous exercise? You all just went for the values that were given? Did you try to change the architectures? Hyperparameters? You can unmute yourself and speak up. I just need one answer. No is perfectly fine. Okay. Or thumbs up, thumbs up means I can infer that you tried. Okay, I didn't see. Okay, so let's get into it. So I assume you did a Git pull, right? So if go into this directory, right? So do you see my screen? I'm gonna bring it to my, you can just put a Git pull, pull this. Mine is already up to date. If you didn't, should do that so that you can get this new directory, 08 Hyperparameter Search. Okay, assuming you already did that, you're going into the notebook. The slides I presented, it's already here. Thanks, Sam. So we can go and look at the first tutorial, which is on hyperparameter search. I want to take it really slow. We don't need to cover both of them today. Even if we spend time on hyperparameter search and try to understand this, then we can take the neural architecture search as a sort of a homework. You can try that notebook and if you have questions, you can get back to me. But I want, instead of rushing, I want to make sure we get at least one thing right and clear. Is that fine? Okay. So again, the drill, make sure you have Conda 2021-1130. So you can go and check the kernel, change the kernel. If you don't see that kernel, choose Conda 2021-1130. So that should be your kernel. We have DeepHyper already installed in that kernel, so you can directly use it. You don't need to do any install. Of course, we do have this command. It will just check and say the different dependencies are already there. But it's a sort of a sanity check that everything is okay. So I'm going to do restart and clear output. My cells are all clear, so we will be executing this together. Okay, so the first cell, the usual thing, we do install DeepHyper for the notebook. And the second thing is, this is again something to do with the Jupyter notebook. So for the, this is something that you won't do it when you submit the jobs and things like that, but you need this for the Jupyter notebook because the async IO does not allow the nested event loops, and Jupyter is using something called Tornado. So there is some sort of conflict. This is something that you should not worry about. Just say, this is for running the Jupyter notebook with DeepHyper. And import OS. Okay. And we will be importing TensorFlow. These are all the usual imports. Oh, so so this import Ray. So Ray is a workflow system, which basically says, okay, I have a search. So it's the search is now sort of configured in a manager worker paradigm, which means that the manager runs the search, okay, and it generates configurations, and the workers receive those configurations, and each worker can train a model based on the configuration that it receives. When I say configuration, configuration is a vector of hyperparameter values, which can contain learning rate, batch size, type of optimizers, and so on and so forth. Okay, so that's what each worker will do. So here we will be using Ray. So it's importing. And then there is a code to detect GPUs. See, it says 1 GPU available. So we'll be using 1 manager and 1 worker. Okay, we can be configured like if you have 100 nodes, right? You are 1 manager, and you will have 1 manager on 1 node and 99 worker nodes. Okay, which means that you can generate 99 configurations in parallel and evaluate them, and as soon as one of them finishes, you can give, the workflow system will take that and put it into the manager, from the worker to the manager, and the manager will go and generate another configuration. So that's why we call this as an asynchronous manager worker framework. So the data set that we will be using for this tutorial is from the Cleveland Clinic Foundation for Heart Disease. It consists of patient features such as age, sex, chest pain type, TRESS, BPD, that's a resting blood pressure, cholesterol, etc., etc. So these are all the input features, and you can see those descriptions. And here are the feature type, which says what is numeric, what is categorical, and so on and so forth. And we will be using these features to predict whether a patient has a heart disease or not. So which is it's a 0 and 1, which is a binary classification problem. So what we want to do is to predict based on the features given whether the patient has a heart disease. Okay. So the data set is already in the directory. So we will be loading that. So the data set is in the CSV file format. It's hard.csv, and we just load the data and split that into training data and validation data, right? So we will use a fraction, 20% as a validation data, and the remaining 80% as a training data. Okay. And then, of course, you all know, right? So, TensorFlow, you work with the TensorFlow Keras, the input features should be all numeric, right? Even though we have categorical features, right? We cannot handle categorical features directly in TensorFlow or in Keras, right? So we have to do encoding, and there are different types of encoding that one can do, and we basically, this cell is all about converting. These are the functions that to encode the numerical features and encode the categorical features. So we have two different functions. It basically takes the numerical features and encode them. And because the numerical feature here doesn't always mean, you see the resting, so this one, right? Although the values are 0, 1, 2, they are categorical type. So we should not consider this as 0, 1, 2. So that's why we have a function that takes a numeric value and encode them properly. And you also have categorical values that need to be encoded. So those are all, those are the functions to sort of, convert those categorical features into numeric features. All you need to know, or you can go and play with that, but essentially this is about converting them into numeric features. Okay, can execute that cell. Fine, so far so good. And here is where we define what is called a run function. A run function is a function that takes a dictionary of hyperparameter values, evaluate them, and return the validation logs, right? The validation metric that you want to optimize. So here you can see what we are doing. So we are taking the training data, and we are saying what is the batch size, right? And we do the categorical features encoding using the function that we defined above, categorical feature encoding, and we have the numerical features, right? All these, converting the data into the proper format, and then we take all those columns and put them into sort of a matrix, right? Again, these are all features. Okay, so these are the concatenation. So basically, this is the input layer that concatenates all the features, right? So you need the input layer that takes all these features, right? So that's what it is. But the interesting thing here is, these are the things that you do even for normal model training, right? Fine. But here is where the configuration function differs from the normal model training. So basically, you define a dense layer without actually specifying the actual number of units, right? So you say config of units. Basically, config is a dictionary that you will pass to this function, and you'll use the units from the config dictionary to set the number of units in the dense layer. Similarly, you take the activation function value from the dictionary and set it to the activation. So, the logic is simple, right? So in the dictionary, you will have, in the Python dictionary, you will have units, activation, dropout, and what you want is, everything remains fixed, and based on the dictionary value, you will change the hyperparameter values of the neural network, right? And then you optimize. Again, in the optimizer, you will see the config of learning rate. So learning rate is something that we are going to pass as a hyperparameter. And the metrics, these things need to be fixed, right? So binary cross entropy and metrics, this need to be fixed. But learning rate is a hyperparameter that we want to optimize. And the number of epochs is again a hyperparameter that we want to optimize, right? So we try to say, we sort of parameterized the neural network based on the dictionary value that we are going to pass. So everything else remains the same, but the neural network units, dropout rate, learning rate, number of epoch changes based on the dictionary value. values in the dictionary. Okay, so and then we take that and then we train. So this is just a function, right? So we are not training them. We are not actually training the model. We just define the run function in this way. Okay. And then the first thing to do is, just not sure we ran this. Yeah, make sure you run this. Okay, we ran the 7, and then we are going to execute 8. And then, so we define the run function. Now we want to just go and evaluate that run function, right? So you can set the units to 32, activation to ReLU, dropout to 0. This is, again, this is how we sort of do the sanity check, right? You can go and change 64. The network will be trained for 64 units. Feel free to try and say and report what is the accuracy values that you are seeing by changing the units from 32 to 64, or from dropout from 0.5 to 1.0 or 0.9, which is like high value, and see what is the accuracy that you are seeing. We can also do this. Just note down this because we will be improving from this. But let's say if you do 0.9 dropout, does it change significantly? Yeah, 0.78, right? It fell from 0.8 to 0.78, right? So how about just doing like only 8 units? .7. So this one doesn't have a lot of impact, but that's fine. The batch size can have impact in learning rate. So please change the batch size, learning rate, or units, and can you post it in the chat? What are the values that you are seeing? Anyone? I don't see any chat message. Bethany, did you see anything?
Yeah, I don't think they have access to the chat and Zoom directly.
Oh, okay. So probably they can. So the only way they can chat, type in is through the Zoom. Through Slack, right?
Yeah. So we've
okay.
been encouraging Slack instead of.
Oh, okay.
Zoom.
I can pull up.
So I see some people are chatting.
Okay.
Or
Sorry,
typing.
my bad. I was not watching the chat. We can wait a couple of minutes. Please post some values in the Slack, and we can see what different values that you are getting. Also post the hyperparameter values that you use to get that accuracy value. Okay, 0.83 from Shinhu. Shasha said 0.803. Batch size 48, right? So that's an interesting value, right? So typically people said batch size multiple of or power of in power 2, right? Batch size 64 gives error. Okay. 16 units, 0.787. Okay. This is great. So you already saw, right? So by changing these values, you can vary the accuracy in a reasonably in a significant way, right? So that's the point I want to make. Like these values matter, and yeah. So 10 to the power minus very small learning rate, bad. 48 batch size learning rate, e to the power minus 2, 0.82. Great, thanks for trying. This is great. So this is to illustrate the point that these values matter, right? based on how you said, even for the simple data set, right? So for 300 rows and the simple network, like how many layers? Only one layer, 2 layers. For these 2 layers, we are seeing significant differences in the accuracy. Think about when you are dealing with really large scientific data sets, you know, with the tens of layers, and when you have that sort of complexity, how these values can really, you know, break our break the learning and break the accuracy and so on and so forth. So that's a point I want to make. Again, I thank all the participants for trying out different values. This is great. Okay, so now the question is how we can, you know, instead of manually trying to figure out what these values are, you know, can we use the software, you know, software such as DeepHyper and Hyperparameter Search to do this automatically and come up with good values for these hyperparameters. Okay, so let's proceed. So this is how we define hyperparameter search problem in DeepHyper. Okay, Yufeng said that size accuracy 0.86. Oh, okay, so this is better, right? This is the best so far. Great. So, but look at the batch size. It's pretty weird, right? It's 53. Cool. Very nice. Is 53 your lucky number, you think? Okay. Anyway, so this is so this is how you define the hyperparameter search problem. So which is like, you know, you from DeepHyper.problem import HP problem. You know, it's like, okay, HP problem is a problem class, and we are going to add 2 hyperparameters, which is the number of units and the number of epochs. Okay, and we say, okay, these are 8 to 128. This is a lower bound, and this is the upper bound, and we are going to consider all possible values. You know, so this is a discrete hyperparameter, all possible values from 8 to 128. It automatically infers this is integer parameters because we don't put .0, right? So all values between 8 and 128, and we consider it with equal equal importance. We are not saying that, oh, you know, consider 64 more important, or, you know, around 64 more important than 8 and 128. No. In fact, we can do that. There is a way to sort of specify that. You know, instead of saying uniform prior, you can say normal prior and give some value. But let's make these things very simple, saying that consider all possible values between 8 and 128 with equal probability, right? The number of epochs that can go from 10 to 100, right? And the activation function, right? So we say we define activation functions. So these are all possible activation functions that we can choose. Okay, ILU, GILU, hard sigma, linear, ReLU. So, you know, more often, like, you know, people just, you know, stick with 1 or 2 activation functions. The power of this automated search is that, you know, you are not sort of constraining yourself to just this 1 or 2, like if I'm choosing 53 as a prime number, right? So you want to have more possibilities and see if you can really improve the accuracy. And so this is saying, like, okay, consider all these activation functions, okay? And then you define that as a list and say problem.add hyperparameter activations, and this hyperparameter name is called activation. And then we add real hyperparameters. Again, you know, we give .0 to say that it is, you know, so that it automatically infers that it's a real value, not a discrete or integer, or not categorical. So these are all considered categorical, right? So this is a dropout rate that can go from 0.0 to 0.6. Okay. And here is again, you know, we are going to define the batch size and learning rate. Add hyperparameter 8256. Log uniform batch size. So we define a prior called log uniform. So let me explain why that is. But we basically say batch size goes from 8 to 256, but it is not uniform. Similarly, learning rate goes from e to the -5 to e to the -2, right? Again, it's log uniform. Anyone have an insight on why we define a prior of log uniform instead of uniform? Why we need to consider log uniform instead of uniform? Anyone?
Someone's typing.
Yes.
Yeah, you're getting some
Yes.
answers. But yep,
Yes.
yep.
I think I see Shasha typing in. So essentially, previous all those parameters we said uniform prior, right? Which means that the search considers all these values with equal probability. Let's say 10 to 100, any value between 10 to 100 has equal probability, right? While searching. So the scale is really the right answer, but there is also sort of a subtle aspect in addition to the scale, right? The reason why we want to consider learning rate with the log uniform prior. So log uniform prior means you will have high probability in this range, right? So 10 to the minus 5, 10 to the minus 4, you will have a lot more possibility to sample from 10 to the minus 5, 10 to the power minus 4. So the distance between 10 to the minus 5 and minus 4 is much bigger than 10 to the power of minus 2 or e to the power minus 2 and e to the minus 1, right? So if you don't specify log uniform, and if you just specify uniform, which is the default, what happens? You will go and randomly sample learning rate values from this interval, right? E to the power minus 5 to e to the power minus 2. And we know that if you do, then half of them, right? Half of them will be, let's say, about 10 to the power minus 3. And we all know that we need to have a lot more values, at least for this data set, a lot more values that need to be sampled in the lower learning rate range rather than the one at the higher. More importantly, you don't set learning rate 1, right? Or learning rate 100. No one prevents you from doing it, but eventually that results in gradient explosion, right? A small change, you multiply that with the step size, and your gradient tend to explode, right? So you don't want that. And when you're talking about stochastic gradient descent or stochastic gradient descent variance in a high dimensional space, you want to sort of make careful steps, right? Instead of taking large steps, right? And that's why you say, okay, I do specify the range, but I want to bias my samples more towards the lower end or lower spectrum, or the lower values of the learning rate as opposed to the higher ones, right? So that's why we are sort of defining the log uniform scale instead of uniform scale. So if you say uniform, then these lot of learning rate values will not be as good as the one with the log uniform prior. Is that clear? If it is not clear, I will explain it again. Please let me know. The issue of defining right prior, it's not compulsory, but it can really improve the efficiency of hyperparameter search, especially if you're talking about learning rate, right? You don't want learning rate, a lot of learning rate. So let's say you can always define, another way to explain this is, okay, so you define lower bound 0.0 to 1.0, okay, learning rate. And if you just blindly sample, half of your samples will be above 0.5, right? And that you don't want to, right? So in the sense that I don't want half of my samples, I don't want to put a lot of emphasis between 0.5 and 1, but I want to have a lot more samples from 0.0 to 0.5, right? So that's why you define that sort of log uniform prior. Correct. So Rui is making a good point. It depends on the models. Correct. It depends on the models. It depends on the data set, and more importantly, it depends on the loss surface, right? If your loss surface is pretty smooth, convex, etc., you can afford to do large learning rate. In fact, in many of the cases, you will have sort of a learning rate schedule that sort of in the beginning you will have large steps so that you don't get stuck in poor local solution and try to improve there, cannot get out. So what we usually have is a sort of a learning rate schedule, which you can parameterize and then do a hyperparameter search on top of it. But essentially, you start from a large learning rate, and as you move, you will sort of reduce the learning rate, right? The learning rates, the schedule in which you reduce that can be a hyperparameter, and that one you can tune, right? So you can think about those possibilities as well. And the typical strategy is you start with a large learning rate and then reduce it to a smaller one, and then you try to restart, do a sort of a restart in which you again do a large step and then reduce it and do this in a cyclic way. So that is robust in many cases. The other question is, do you have a fine-grained sampling mechanism if users have some pre-knowledge about the model? Yes, you can achieve that with defining the prior and reducing the bounds. So those are mechanisms in which you can leverage your knowledge about the model and either constrain the search space or make the values of the possible ranges for a particular parameter really small, and you can that can certainly help the search, so to speak. So instead of log normal, so instead of uniform prior, you can use normal prior, right? The normal prior basically we didn't use here. You can use normal. The normal prior basically says, okay, I know the best value, but I want to search around my best value, right? And you say, okay, my normal prior mu is this and sigma is this, right? And you said my mu is, let's say, e to the power -3, and I want a sigma with the 0.001, right? In that, if you set that prior, the algorithm considers the samples from that distribution. It's not necessary, but if you already know, that's a very good strategy to use. Okay, is this clear? How to define the problem? So it's all we are saying is, what is our space? What is our input space looks like? That's it. Okay. Okay. What did I do? Did I change? Trying to set illegal value of 0 hyperparameter dropout. Haha. Okay. So we do have some. So you see, this is a sanity check, right? So basically, we define the dropout to 0.0 and 0.6. So that's a maximum allowable range. But here I sort of changed my dropout previously to experiment with some other value. So that's why it's throwing the error. So it just go and sort of checks the default configuration is within the bound. Perfect. This is good, right? So basically it says, okay, uniform integer between this range on batch size that is on the log scale, learning rate, units, type. So essentially, it prints our search space. Okay. Okay. So now we are going to define the evaluator. So evaluator basically, takes the run function and run it on the GPU. How to evaluate, use the workflow system and run it on the GPU and get our results back. So so it says, okay, so the number of CPUs per task, we all set this one. For the tutorial purposes, we assume that we have one worker, this because we are using only one GPU, and one worker per evaluation, right? So each worker will evaluate only one model. So let's keep at that. As you know, each node has multiple GPUs, right? And if we can use, if we have set this in such a way to use multiple GPUs, then we can use those things as well. So those are the arguments for this. But typically these are taken care, when you are running the job actually on the ALCF systems, the workflow will take care of this, and the workflow system will take care of this. But for the Jupyter notebook, we have to set this manually. So you don't need to worry too much about this. Okay, so here is the pseudocode of the asynchronous model-based search Bayesian optimization. So the way that the search algorithm works is, it begins with random sampling on the space that we define. Okay, and then it samples excess configuration. So excess is the number of workers that are available. If you have one worker, it will sample one configuration. For the random sample, it will generate multiple, but as you move down. So the random sample, let's say, this is a user, this is an algorithm defined parameter. So in the beginning, it samples 10 random configurations from the space and send that to the worker. If you have one worker, the 10 will execute serially. But if you have 10 workers, 10 will happen at the same time. Okay, so add eval batch basically evaluates all of them in parallel. While the stopping criterion is not met, what you see is like you wait, right? You wait if you see one of the configuration is finished, right? One of the model training is finished. So if it's finished, then you take those results, okay, and then retrain the model. If you think about what we discussed in the first part, it's basically there is a learning model that sits on top of it and takes those results and learn from it. So it's basically a model fitting that happens at the top. And then it generates a configuration. So you can then use the model M and the domain to generate a configuration that's seen improving from what it has seen previously. And it sends that to the evaluation. So add eval batch basically takes the workflow system, comes into play, takes that, and then send to the worker for evaluation. So this is what this is a search algorithm that runs on the master or the manager node, and add eval batch, whatever you send it to add eval batch, the worker will take it and run it and give the results back. You see, there is no wait. So which means that the algorithm don't wait for any of the evaluation to finish. Of course, with the one worker, you have to wait. But if you have 10 workers, as soon as one is finished, you take the results back, refit the model, generate a new configuration, and send it to the worker to fit it, right? So this is critical when you are doing hyperparameter search at scale. Otherwise, even if you have a batch, let's say, okay, I want to evaluate 30, I want to wait 30 to be finished, because each configuration or each model training can take different training time, right? So depending on the number of units and different layers, and in fact, if you are trying to tune the number of epochs, the runtimes vary between different model training. So you don't want to do this in a batch fashion. You want to do this in a completely asynchronous fashion. And that's one of the critical challenge for doing hyperparameter search using Bayesian optimization at scale. Okay, so here are some algorithm details, which I'm going to skip. At the moment, it's not very critical, but what is critical is what is the model? You could ask like, hey, how do you learn the relationship between the input configurations and its corresponding validation metric, right? So currently we experimented with the various types of models, including Gaussian process regression, random forest, extra trees, and we settled on random forest because of its low computational overhead and its ability to model mixed integer space, right? So the hyperparameter space that we are working has integer parameters, categorical parameters, and real parameters. And the algorithm that seems a lot more robust to all these three is random forest. And these are some experimental comparison between different algorithms. And here I want to ask the participant another question, like why we cannot use deep learning for this purpose? Why we cannot use a deep neural network for learning the relationship between the hyperparameters and its corresponding validation metric? Anyone? right? So all we need is a predictive model, right? So we use the predictive model to identify what is a promising configuration, which we haven't evaluated, right? So it's basically any predictive model will do the job. And why we are not using random forests? Why we are not using deep neural networks here? Right, so we spent significant number of lectures, studying about deep neural networks, right? Why we cannot use that for this purpose? Excellent. Yes, Rui, you got it. So the training time could be one factor. The other thing is, often you might need more data. So you can, of course, switch to a neural network at later point of time when you have more data. But then again, the training time will be a factor. So we need something that is fast, that can handle mixed integer space, and that can be trained faster, right? So those are all the different metrics that we use, and in a small scale, people often use Gaussian process regression, but at a scale it doesn't work because the retraining time becomes prohibitive. Let's say if you are working with hundreds of nodes, and if you use Gaussian process regression to learn this, it becomes computationally expensive. It won't scale. And you need to find the right kernels for the mix. So Gaussian process regression depends on kernels. How do you handle the integer and categorical variables? It's pretty, it handles smooth, all continuous variables, it handles it very well. But as soon as you throw in integer and discrete parameters, you have to come up with the right kernel, and often that's a tricky. So random forest, it's a lot more sort of robust for these kind of things. And all we need is, we are not trying to use the model to do some critical prediction. All we need is some way to identify what is a good region in the search space, what is a bad region in the search space, try to avoid the bad region and sample from good region, and do that fast. And that is the key. Okay, any other insight? Yeah, so we used the HB is the hyperband. We sort of compared that to the hyperband. Hyperband, one challenge that we have to overcome in hyperband is the following, right? So it's sort of a batch synchronous. You need all the hyperparameters to be finished so that it can go and do the next batch, right? So it's sort of successive halving. You cannot half the number of configurations without sort of finishing. But there are some recent works on how to do that in an asynchronous way. But this is the sort of the benchmark that we did with hyperband previously. So it's it works well for let's say you have a university cluster, 20-30 nodes, and the system utilization is not a critical factor, then and a reasonable number of hyperparameters, you can do that. But again, hyperband relies on more randomly sampled hyperparameter configuration. So if you have a large search space, you have to sort of come up with a way to define your search space that is amenable for hyperband. Okay, so let's get going. We are pretty close to the time, but again, as I said, let's spend the time on just hyperparameter search and leave the neural architecture search for homework. But I'm happy to follow up. I want to make sure that we all get this one ready. So this is some helper on an asynchronous model-based search. Things like, okay, then, once so all we need is to define the search space, right? Define the evaluation, how to evaluate a configuration. And once we defined all this, then we are ready to run the search. And you have the maximum evaluations of 10, go and change it to 30 or 50 or whatever. And then, I just do it with, let's say, 20, so that we get results quickly. So max evals here basically means how many neural network evaluations that we are doing. So here I'm saying the stopping criteria, like, okay, evaluate 20 and then stop, right? See, so far, manually, we got to 0.83, right? With just this on a notebook, we already reaching 0.85 and 0.86. Okay, so yeah, we stopped with 20. Of course, you can set it to 100 and run it for a while. You will see improvements. But think about it, right? With just 20 evaluations, in no time, we sort of got to a 0.86, which is better than what we could achieve so far manually, even with the Eufem's prime number for the batch size of 53. So so essentially, there are two things, right? So one is it sort of takes out this trial and error process to set these parameter values, right? So you can just automate that and be more rigorous and systematic about setting those hyperparameter values, because when you start doing this for real, right? So to solve real problems, this can easily take a lot of your time, and you never know the accuracy values that you are getting is because of the low accuracy values that you're getting is just because poor architecture, poor data set, or poor hyperparameter values. The last thing you want to make sure is it's not this hyperparameter values that is affecting all your new architectural innovations, right? With this, you say, okay, here are my architecture. I want to go and get the maximum I could get with this and see how it works. And often we are surprised to see in many cases that it can, even if we take the baseline and fine tune it, we can get really good performance. And that's and we get this, without a lot of human effort. Okay, and then yeah, so you can basically search. So it's not like one time, but you run it like, so we ran it 20 times, right? Oh, sorry, I ran it again. But anyway, so and then see what the accuracy values are. You don't need to restart the search. If you have access to the object, you can another say like 5 or 10, and then continue from where the search left, right? So that is pretty convenient when you want to do this in an iterative way. In terms of large job, you can just save the search object and reload that object for your next job and set the maximum evaluation. Let's say you already ran it for 1,000 evaluations, and now you say, oh, I want to do another 100 evaluations. You can say you load that object, search object, and then do another 100 evaluations on top of 1,000. It's not like you lose what you did already. So that one, and you can and then print what is the best configuration that you got so far. So this is the restart functionality that I mentioned. Basically, you can So this one is within the same job, you can continue. This is something that you say, okay, I can restart from checkpoint, because often you have limits on how many hours that you can run, right? So doesn't need to be the hyperparameter search job, doesn't need to be only one-time job, right? So you can run it for 8 hours, save the object, and then run the second job with what you have done already. So that's the checkpointing functionality. So essentially, you can see units. So I printed the best configuration we found so far, which is 0.869. This is the new one, right? We almost got 0.87. And it was trained in 2.56 seconds, discovered after 658 seconds, which is not a lot of time for the simple data set, right? So activation ReLU, batch size 256, dropout 0.02538, learning rate 0.0097, number of epochs 10, units 37, and this is the 13th configuration. So this is the best value that we got from the hyperparameter search, right? So and this is a restart functionality, and you can just go from there. You restart, and then you do another 10 evaluations, and printing the best configuration. The other thing that I want to mention is conditional hyperparameters. Okay, so the conditional hyperparameters are basically some values of the hyperparameters are enabled, or even some hyperparameters are enabled only when certain values of other parameters are there. Okay, so so far we use only one layer, right? Now we are going to say we are going to do another layer, which is the dense 2 layer. So previously we have only dense 1 layer. Now we want to do dense 2 layer, and we want to make a search space in which we say the decision to include the dense 2 layer is left for the search. The search can decide whether to include the second layer or not. So that's a 0-1 decision. It's a binary decision. If it includes that dense layer, then it can go and set its units and activation function. You see the hierarchy? So the first thing is, the dense 2 units and the activation is valid only when the dense 2 becomes active, right? Only when the dense 2 is set to is enabled. So that's what the conditional variable or conditional parameters here mean. So that's one thing that DeepHyper is sort of differentiates itself from other existing softwares. It's easy to define a search space without any constraints, but ability to define these type of constraints happens in many cases, and we want to handle that. So this is again, run with condition. So we define the run function, and we use a constraint modeling package called config space to express those constraints. And the way that we can express those constraints are pretty straightforward. And you can see now this is the same hyperparameter space that we talked about previously. Now we say, now we are going to say dense 2, right? It's a second dense layer. We say true or false, which means that it can either take true or false, okay? And the dense 2 units can go from 8 to 128. Activation are the same activation functions that we use for the dense 1 layer, okay? But here are the conditions, how to express those conditions. So the HP dense 2 units, right? That is this hyperparameter becomes active only when HP dense 2 becomes true. Otherwise, the search algorithm will not set any of these values, right? Similarly, HP dense 2 activation, this hyperparameter is active only when the HP dense 2 hyperparameter is set to true. So essentially we are saying when HP dense 2 is set to true, then go and set the values of these two. Otherwise, you cannot set those values, right? So that's the sort of conditional, we call this as a conditional search space in which one hyperparameter is enabled, or one hyperparameter values are enabled only when its upper level hyperparameter is true, or it takes certain value, and so on and so forth. Okay, and this modeling constraints is very powerful as you start building a lot more sophisticated neural architectures and hyperparameter space. So here is a simple example. So we evaluated that, and then we can go and run this. And we are doing that with just 10 evaluations. You can go and change the max evals and see how things change. Okay, so you can, 10 is not enough here, so we can just go and do more. I'll set it to 100 and see how this evolves. But yeah, now we are, see, so when we said max evolves 30, it's actually starting from 11. It's not starting from 10. So it sort of, has the memory. It checks if the object is already there. It reuses whatever that is available. Okay, so anyone with best objective better than what we see in the screen, 0.86, 0.86885. Please type in. Or you can go and add more layers and play with this. How reliable is DeepHyper, and how do you test its reliability? So we do a lot of tests on the benchmarks. We have deep learning benchmarks. So if you're talking about its ability to improve from a baseline, there are many aspects to it. But if you're talking about the software, its ability to run well at scale, and so on and so forth, that's something that we do tests. Whenever we introduce new features, we also do some tests. But having said that, it's we try to balance both the research aspect and the production aspect. We try to put the features that we are most confident about in the main branch, in the production, but there are a lot of research features, so to speak, and that one, if we make it available in the develop branch, and we ask our friendly users to test it, and they give a lot of feedback. We rely on them, and so it's both based on our own internal tests on benchmarks such as Candle, ECP Candle benchmarks, and applications that people are running. Does that answer your question about reliability? And as I said, we do have a community here, and they test the software, and even bug fixes. There are bugs that we can fix quickly. People do that, but if there is a bug that cannot be solved easily, then we also prioritize and try to address that. So it's a mix of testing plus community feedback. But it's open source. Anyone can download, play with it, contribute. We do have a lot of ideas, a lot of new things that need to be done. As you have seen, Bethany already advertised internship portion. It's a very interesting project that for the data subset selection for DeepHyper. So if you're interested, please reach out to her. Okay, so how we are pretty close to the end. How does the optimization of hyperparameters? In which case, Shasha? So if you are talking about the, how we are searching different how we are optimizing the hyperparameters, that's using asynchronous Bayesian optimization. Essentially, there is a, so there is a search algorithm that generates configurations, evaluate them in parallel, and take the results back. Oops. Okay, so we are done. It takes that back and retrain the model within the search algorithm, and use that model to identify promising configurations and sample send those promising configurations for evaluation. And this is done iteratively and in an asynchronous way. So that's how it is searching over different. It is searching over the hyperparameter space. Does that answer your question? Yes, RL can be used. So we have tested, or we experimented RL in the architecture for the neural architecture search, which we didn't cover, but there is a notebook that you can definitely go and look at and play with it. So one thing about RL is, it has a lot of exploratory component, in the sense you need a lot of exploration in the beginning to identify good regions, and then focus on that search space. And what we found out is, compared to the aging evolution, which is completely asynchronous, it doesn't have any gradient descent or whatsoever computationally expensive process in the sort of the master side, right? So manager side, it can generate configurations really fast and fill up the nodes, and that tend to be much more effective as opposed to RL. We implemented a distributed RL that spanned across 1024 nodes on Theta. There are several bottlenecks that we need to overcome. in particular, how to take the gradients from each RL agent. So the idea there is we will have RL agents, several RL agents, and each one of them generate configurations or generate architectures, and they are evaluated. And there is a sort of a central manager that takes the gradients from each of the RL agents and do a sort of synchronization or sort of aggregation of the gradients and send those gradients back. So we attend a HUIGO's distributed data parallel training. So think of distributed data parallel training, how the gradients are sort of exchanged. Similarly, RL agents exchange gradients in their updates. And the point is, RL, at least the proximal policy optimization, the state-of-the-art RL, one of the state-of-the-art RL method at the time didn't scale as much as we want, and it had a lot of exploration. So it sort of lose to the evolutionary aging evolution, asynchronous aging evolution that we implemented. So we did some benchmarks. We showed, in fact, its ability to quickly identify regions in the search space and use them and leverage them as fast as possible at scale. Eventually results in a lot more high quality neural network models compared to the one with a lot of exploration. So eventually RL sort of caught up with the aging evolution, but it took some time. As you know, RL without any prior knowledge, it is sample inefficient, and if you need to find a way to bias it in such a way that you address the sample inefficiency problem. So those are some challenges that we are still working on. So now we are focusing on some different form of RL. It's extremely scalable RL, and it's not in the main branch yet, or not even in the developed branch. But this is another thread, but more on the research side, not in the main branch of the software that you can find. But hope we get some interesting results on that front, and we'll be able to share with everyone soon. There's a SE20 paper where we compared aging evolution with proximal policy, asynchronous proximal policy optimization, and you can find that in the website paper, and also it's available in archive. So where we explain why RL, although it eventually caught up like after 2 hours to the accuracy of aging evolution in terms of computation time, aging evolution seemed better in this case. Okay, other questions? In the single GPU case, it is using only one worker. It is not using multiple workers. But there are scripts in the ALCF website you can follow and sort of launch a job with 10 GPUs, for example. Or if you are using Theta, you can do that on 512 nodes. And we are working on porting DeepHyper on Polaris, our next machine that Bethany mentioned in her talk, where you will be able to play with a lot more GPUs, hundreds of GPUs, 100 workers, or more than hundreds of workers, training models simultaneously and sending those results back to the manager, and the manager generating configuration. So we will have the scripts. Once the machine is up, Polaris is up. We'll definitely put out more information and tutorials on that front, and you will be able to do that. On the notebook, since we are using single GPU, it's only one manager and one worker. So there's no parallel evaluation happening now. Great questions. Please try this out. And also you can see, okay, I don't know whether I will be able to show this. Okay, I can show this here. do check out the neural architecture search. It's a lot more fun, I would say. That's why I wanted to save that for your homework. In particular, you can just go and sample random neural networks with that simple search space that were defined, and see how how different those architectures are. It's really like, there's one thing about, it's fun to generate human faces from the generative models. It's also fun to generate neural architectures from the random, from the search space, random neural architectures, and see, what are the possible architectures that you can get with this 20 lines of code. This is a ResNet like, with skip connections and things like that, and I'm sure you will find it interesting. It's self-explanatory, and there are a lot of details. This starts with some sort of simple data generated like this. It's a linear sum, and we will be doing a neural architecture search to find the best architecture to fit that data, and change that with other type of data set that you played with in the past or you have in your coursework, and see you can generate architectures that are new and novel for the particular data set. Okay. Questions? And I believe Sam already uploaded the slides. Yes, so he did it in the markup. I will also send him the PDF or something like that, and he will be able to commit that here, or I can do that later today.
Great, thank you. And you guys we have the single GPU queue available for the next 11 minutes if you guys want to keep experimenting or try out the neural architecture search. And I think at least a few of us will be around to answer questions in Slack if you come up with more questions.